On behalf of World Energy Reports, we would like to thank you for joining our webinar today. Please feel free to submit any questions you may have, and we will reply by email after the webinar. Thank you.
Hello, my name is Philip McBride, and today I'm going to take you through the Outlook for Offshore Wind Power, a report and database developed by World Energy Reports that addresses the exciting possibilities of offshore wind. As we enter the fourth decade of offshore wind, we see that some markets have moved all through the development cycle, from technology demonstrators to full gigawatt plus scale industrialized wind farms that are becoming cost competitive with fossil fuels and creating growing supply chain opportunities. At the same time, there remain some high potential countries that have yet to embrace offshore wind, often due to the competition of available low-cost fossil fuel source alternatives. We believe that we are at an inflection point when offshore wind can become a more general global play. At a high level, today, we will address some of the major themes and takeaways from our report, such as where offshore wind sits in the electricity generating capacity mix and how we see it achieving a much larger role. We break down current CapEx and OpEx costs, addressing the cost competitiveness of offshore wind. We take a look at the potential for specific regions and countries. We address the opportunities for the supply chain, the exciting subject of wind to hydrogen, and the frontier floating wind turbine technology that is reaching commercial scale and that can help developers tap huge, high quality wind. So why are we interested in offshore wind? It currently plays a relatively small part in the global electricity mix. We will see just 25.5 gigawatts out of a total 6,400 gigawatts of total installed generating capacity comes from offshore wind. But the sector is growing strongly, almost 40% in 2020 and 2021, even with the impacts of the coronavirus pandemic. As capacity grows, the CapEx cost of offshore wind continues to become more and more competitive. Offshore wind is an unlimited resource that can potentially meet global electricity demand. In simple terms, there is a huge project activity potential. Renewables account for some 32% of today's global generating capacity, but offshore wind currently provides just over 1% of the renewable supply side capacity. Onshore wind and solar are well established, accounting for around 45% of renewables capacity and are still growing. But offshore wind is growing at a fast rate, certainly much faster than onshore wind. Global installed offshore capacity stood at around 25.5 gigawatts at the end of 2019. We forecast that the sector will exceed 41 gigawatts of installed capacity by the end of 2021, even taking into consideration COVID-19 effects. Offshore wind activity is likely to maintain close to pre-COVID-19 forecasts, whereas onshore wind projects are likely to see negative growth. Key European offshore wind markets are continuing in their pre-coronavirus completion of projects under construction and running announced offshore wind lease auctions. We see around a 3 to 5 month impact from the coronavirus pandemic on European projects. China is having to restrain its overheating offshore wind project activity, but project activity in 2020 and 2021 is likely to remain high, driven by a 20-year full subsidy benefit milestone of 31st December 2021 grid connection. The US is likely to see around a 12-month delay on earlier plans to some of its significant offshore wind pipeline through coronavirus and EIA issues, with 2021 potentially proving to be a pivotal year for project sanction for the US offshore wind market. The levelized cost of energy, or LCOE, is the average total cost of building and operating the asset per unit of electricity generated over an assumed lifetime, a good way to benchmark the project competitiveness of different fuel sources. Offshore wind LCOE is reducing, witnessed by historic and current auction prices, and puts offshore wind in the competitive band with fossil fuels in the European and Chinese markets. The current global average capex cost to build a utility scale offshore wind farm and distribution system is around $3,000 per kilowatt, with costs reducing by a factor of around 15% every time global capacity doubles. Our capex forecast in the report looks at 3 future capex cost scenarios. Lifetime recurring OPEX accounting for close to 45% of the total lifetime cost of an average utility scale North European offshore wind farm, and provides some interesting potential local port and supply chain benefits close to where offshore wind farms are located. More of that later. The overall global technical potential for electricity generation from offshore wind power is assessed to be over 420,000 terawatt hours. That equates to more than 120,000 gigawatts of installed capacity, significantly larger than the current world electricity demand of around 23,000 terawatt hours, or around 6,400 gigawatts total installed capacity. Close to 80% of the assessed technical offshore wind potential is in deep water, supporting the interest in the floating offshore wind segment. The balanced global 20% of shallow water technical potential still accounts for a capacity of over 3.5 times of today's total global electricity demand. The drivers for bottom fixed offshore wind farms remain strong, but the potential for deeper water floating offshore wind turbines is huge. Industry is forecasting that offshore wind will have achieved between 340 and 560 gigawatts of installation by 2040, with a CAGR of 13 to 16%. The key European and Chinese markets will continue to lead market growth, but significant capacity will be added by the US in North America, Japan, South Korea, Taiwan and Vietnam in Asia Pacific region, India and Brazil from other regions. Our database covers some 500 gigawatts of evolving project potential, with Europe, Asia Pacific and North America the most active regions, accounting for some 97% of our pipeline. In terms of CapEx, we see the current identified pipeline requiring from close to $1 trillion to as much as $1.5 trillion. At around $95,000 per megawatt annual OPEX for a North European wind farm, our current identified pipeline could develop into an annual O&M market of $45 billion, covering onshore support bases and offshore operations, repair, maintenance, and logistics operations. So where will the activity be? Well, we've seen the key role of the European, Asia Pacific, and North American regions. We will now demonstrate at a high level how our database tool allows subscribers to drill down from region to country and specific project levels. As a first step, you have to log on with the details provided to you once you have a license. So when you log on to the database, you come to this home page. On the home page, it's made up of the map section, some high-level analysis, the full database of all the projects, that's over 2,000 project entries in the database, and a range of filters that you can apply as you use the tool. So let's, at a high level, just look at how it works. First of all, if you want to use the map, you can just scroll in. Let's scroll in on the UK, one of the big markets. You can see all the wind farms marked up. These purple ones are the operational wind farms. So if I want to click on this one, Hornsea 1, it takes me to the database where I get the project overview with main project details, some of the site details, including the map where it is, the type, fixed or floating, some information about the turbines, the turbine OEM, how big they are, how many, and the structure involved. And at the bottom, we list some related wind farms, and this is based on geographical criteria. So how can we use the filters to get a more detailed look at the database? Well, let's say we're interested in Japan. First of all, you click on Japan, and that will take you to all the projects in the country. Well, let's say I want to start with development zones, the longer term part of the pipeline in Japan. I can see we have a few development zones. Going down, we can see that they're all listed in the database, which we can click on those and go into them. Let's add the early plan projects. These are not yet consented or seeking consent, but are moving towards that. So we have some of those added to the data. Then we've got the projects which applications have submitted and consent authorized. Let's take away the early plan and development zones to make that clearer for everybody. I can add the projects in pre-construction as well. You can see up in the Akita province, we have some projects, and also the Kashima Port project, all of them listed here. So if we wanted to go into the Akita Noshiro project, we would again get the details, same as we've shown you previously, including the supply chain elements who's involved. Let's have a look at another one of the major markets, or major potential markets, I should really say. We've cleared the filters. I'm going to have a look at the USA now. So in the USA, and this is all the projects, including those that are cancelled, dormant, or failed proposals, worth following in case they come back. You can see a large concentration on the East Coast, the Great Lakes projects, some West Coast, Hawaii projects, and some Gulf of Mexico projects, mainly cancelled. So let's look at the pipeline, the development zones. And we can see where the development zones really are: East Coast, California, West Coast, Hawaii. Some early plan projects also in those same areas. Let's clear that, and we'll look at the applications submitted. These are the projects that are looking to be built. And this is really where the state of the US offshore industry is at the moment. And the applications have been submitted on a large range of projects, and they're going through the process to receive their permits to build. So you've got inland projects or on the Great Lakes, such as Icebreaker. Offshore, you've got Aquaventus as a floating project. You've got the Vineyard project, which is the major pipeline project for the US. This is the one that everybody's waiting on to see if that gets approval to build. Once that does, we should see movement on Bay State, Sunrise, South Fork, Revolution, Empire Wind, and Marwin. We also have in the US a project that's just moving from pre-construction at the moment, Coastal Virginia, to being actually constructed and soon to be generating. So we'll clear those out, and let's see, we want to look at a company and a company's activities. So let's look at the largest developer in the world, which is Ørsted. That will give us a good spread of projects of where they're interested. All the projects in this filter are, all the companies are listed alphabetically. So let's choose Ørsted. If we choose Ørsted, we can see that they have activities in Asia, Europe, and the European projects go from the Irish Sea all the way through North Sea and Baltic. And we can see from this analysis that quickly comes up on Ørsted's activity. Over 55% is based in Europe. And then we have some US projects. So Ørsted is, you can see there is widely involved. And we can see all the details of the projects. If you want to know more about those, you can just drop in, like the Formosa project in Taiwan. Click on that and it'll give you the details about the project. So hopefully that's given you a good idea of how the database looks. Now I'm going to take you back to the main presentation. As you see, the database contains significant functionality to allow for high-level analysis using a range of search variables. In our report, we undertake regional and country-level analysis using the projects in the database, which clearly shows the ongoing potential of the European market, with the UK maintaining its leading position, driven by the leasing activity of Crown Estate for England, Wales and Northern Ireland, and Crown Estate Scotland, the latter embarking on the much anticipated ScotWind up to 10 gigawatt bottom fixed and floating leasing round. Denmark owns the potential, making an interesting market over the next 2 decades. Germany will remain a strong player after a temporary activity slowdown, as will the Netherlands. France and Norway will emerge as active markets, both for bottom fixed and floating, and will be joined by Ireland and Poland. We forecast the ongoing strength of the Chinese market, despite a continuing dominance of coal-fired power plants and competition from gas and nuclear. Renewables, including offshore wind, will play a small but growing element of the electricity generation supply side in China. But the scale of the overall power market means that even if the percentage is relatively small, offshore wind activity remains comparatively high compared to other countries. We see the ongoing growth of Taiwan and the emergence of Japan, South Korea, and Vietnam in Asia Pacific as significant offshore wind players. There is a clear potential for the US East Coast market, especially in federal waters, once current permitting hurdles are overcome, hopefully by the fourth quarter of this year. Federal Waters Leasing Authority, BOEM, has issued 15 licenses by the end of 2019, amounting to over 20 gigawatts of project potential. Of those, projects like Dominion's Coastal Virginia and CIP and Iberdrola's Vineyard offshore wind farms are the likely first movers in East Coast federal waters. The West Coast and Hawaiian federal waters have good longer-term potential and are part of BOEM future auction plans. Inland, the Great Lakes icebreaker is the pivotal project to follow. There are some interesting early stage opportunities in Brazil, including three 3-gigawatt projects, and in India's southwest Tamil Nadu and northeast Gujarat provinces. Now we will have a high-level look at some of the technical developments in offshore wind covered in the report. We will discuss foundations accommodating deeper water projects, turbines and installation vessels getting larger, and transmission substations getting bigger. Projects have increasingly grown in both size and distance from shore. Shallow water is defined as under 60 meters. This is where bottom-fixed foundations are competitive. Low-cost monopiles, the prevalent foundation choice to date, generally are installed in waters which are shallower, but can go up to 40 to 50 meters water depth. And jackets offer a solution as deep as 50 to 60 meters. Floating foundations are an option over 50 meters. Deep water over 60 meters is where floating units are the preferred solution. The three main floating concepts, well known to the oil and gas industry, the semi-sub, SPA, and TLP, are providing solutions to developers to access some of the 80% of technical wind potential that is currently classified as deep water. Monopiles and transition pieces fabrication has been concentrated in European and Chinese suppliers like Black, EEW, SIF Smulders, and ZPMC, to name a few. Jacket fabrication has provided opportunities to European yards and increasingly yards located in the Middle East, Southeast, and East Asia. Turbines are getting bigger and bigger, allowing for the cost benefit of less numbers of foundations and inter-array cables, and allowing for higher availability. Recently, we were talking excitingly about 12 megawatt turbines, and now we are waiting for Siemens Gamesa's 14 megawatt turbine to be debuted on projects in Taiwan and the US. Siemens Gamesa has targeted the offshore wind market and has established a clear #1 position. Vestas, the world's largest onshore turbine OEM, and Mitsubishi formed the MHI Vestas venture specifically for offshore wind. A range of Chinese companies have been developing larger and larger turbines, and although focused on the very hot Chinese market, have been looking at overseas orders. Over the years, there has been significant consolidation in the sector, and there remains room for further consolidation. To date, a real draw for turbine OEMs is a requirement or desire to provide ongoing maintenance services beyond warranty periods, and that can generate positive returns. The trend for larger and deeper turbines is presenting challenges for the installation fleet. Using the Yandanur jackup fleet as an example, it is clear to see the development of requirements in water depth, lifting height and distance, and turbine size and weight, and to be served by a wind turbine installation vessel. With the smaller Taiwan, the one on the right-hand side, being delivered in 2011, capable of lifting nacelles to 100 meters high and operating in 40-meter water depth. And the Volavon 2013, delivered in 2013, capable of lifting bigger nacelles 120 meters high in 50 meters of water. Then you have the Voltaire, new build, is designed for 165-meter nacelle height and 80-meter water depth. As new projects generally use larger turbines, earlier generation wind turbine installation vessels will need to focus on operations and maintenance and repowering work. For bigger turbines and deeper water requiring jacket foundations is seeing heavy transport and heavy lift vessels with cranes up to 5,000 tons capacity. Nearshore is defined as under 50 kilometers, where AC transmission is the most competitive solution, either with transmission using a substation or direct to shore. Under 50 kilometers, HVAC distribution has the lowest cost and can be competitive up to around 100 kilometers. Far offshore is over 50 kilometers, where DC transmission becomes more competitive. High voltage DC solutions offer better performance and lower costs over longer distances. AC substations, when used, can weigh in between around 1,000 to 3,000 tons. And a gigawatt wind farm can require 2 or 3 of these. Many European and Chinese wind farms are currently relatively near shore and rely on AC distribution, either direct to shore or from substations. High voltage DC substations can weigh anywhere from 10,000 to 25,000 tons. In North Europe, HVDC substations are often used as distribution hubs for several wind farms. The large HVDCs, high voltage direct current substations, and their jacket fabrications are now being built outside of destination markets and in yards in the Middle East and Southeast Asia. Much of the focus is on the costs to build a wind farm. But over 40% of the lifetime spend on an offshore wind farm will generally be allocated to operations and maintenance. The need for offshore support bases has seen welcome investment in traditional European industrial and fishing ports, including some that have fallen on hard times, as well as local supply chains. There remains a need to send men and women offshore to inspect and maintain the turbines and the structures once operating and for the duration of their up to 30-year life. And this has driven the growth of the crew transfer, CTV, vessel fleet for nearer shore wind farms, and the larger and costlier, order of magnitude $50 million, service operation vessel, SOV, for wind farms further offshore. I would like to spend a few minutes talking about floating offshore wind due to the huge deep water technical wind potential and the progress being made on some 50 or so concepts. Projections show major floating offshore wind potential. The US and Japan are projected to become major floating offshore wind players in the second half of the decade, along with Norway, the UK, and France. Our report takes a detailed look at the 50 or so floating concepts at various stages of development today. Some concepts are clearly more advanced and are reaching commercial level arrays. The table shows a sample of the leading concept development status, which is explored in detail in our report. An already proven concept on the Hywind Scotland project, Equinor will use a Hywind Spar concept on projects such as Hywind Tampen, featuring 11 8-megawatt turbines, which is due online in 2022. Tampen will supply around 35% of the Sonora and Gullfaks offshore production platform's energy demand, replacing energy generated by gas turbines. Tampen will be the world's first floating wind farm to power oil and gas platforms. Despite the benefits of major assembly ashore, one potential disadvantage for the SPAR concept is the process for mating turbine to hull offshore in deeper protected water, preferably close to the fabrication and assembly yard. We don't see the same challenge for semi-sub concepts such as the leading semi-concept, Principal Powers Wind Float, that allows for onshore or dock hull assembly and dock or quayside turbine mating. and towage offshore with traditional towing and anchor handling tugs. The concept is being tested on the Kincardine project in Scotland and the Windfloat Atlantic project in Portugal, a suitable testbed for potential East Coast US deployment. But it's not all about steel. France's Ideol has introduced concrete to lower construction costs in its damping pool concept. Like Windfloat, the hull can be built in dock or onshore with turbine mating alongside using quayside cranes. Planned to be demonstrated at scale in France in 2021, SBM IFPN's TLP will be the first large-scale offshore wind TLP. Similar to many semi-sub concepts, this one is again constructed onshore or in docks and launched for mating of hull and turbine at quayside. Again, our report dives into the details of some 50 concepts identifying projects in Europe, Asia Pacific and the US, where floating solutions are planned to be used, providing significant opportunities to shipyards, ports, general concrete contractors and traditional offshore support vessel owners. Offshore wind power is not just about providing electrical power to a general grid, or even the decarbonisation of oil and gas operations, as we see with Hywind Tampen, but offshore wind has a role to play in producing clean or green hydrogen. Offshore wind increasing cost, competitiveness and high capacity factors mean that offshore wind farms can contribute to the production of low carbon hydrogen. Projects are moving from the drawing board to demonstration scale as the precursor to multi-gigawatt wind farms whose sole purpose is to provide clean energy for hydrogen production. Electricity generated by offshore wind projects can be used in whole or in part to power electrolyzers that split water into hydrogen and oxygen. Hydrogen as a clean fuel can be used in transport, heating, steel production, electricity and hydrogen-based fuels, synthetic methane and liquid fuels, ammonia and methanol. Offshore wind energy could replace some of the natural gas and coal which is now used to produce around 70 million tonnes of pure hydrogen and around 45 million tonnes of non-separated hydrogen annually, collectively known as grey hydrogen. In our report, we look at a range of initiatives, including some of the more advanced projects in Holland, the UK, Germany and Denmark. Around 70 million tonnes per year of hydrogen is used today, mainly in oil refining and chemical production, but it is almost all produced from fossil fuels. There are multiple solutions being developed, from offshore wind powering onshore electrolyzers, such as Ørsted and ITM's Gigastack UK project, wind powering electrolyzers on oil and gas platforms for export by existing pipelines, concept being tested on the Poseidon project in Holland, and even compressing the gas on the platform for ship transport. And we are seeing plans for electrolyzers to be located on the wind turbine structure, such as Ørsted and ITM study of turbine-mounted electrolyzers as part of the UK-funded project, and ERM's Dolphin project based on Principal Power's Windfloat concept, with the electrolyzers being located on the turbine floating foundation. Around 10 gigawatts of offshore wind capacity is needed to produce 1 million tonnes of hydrogen a year. With 70 million tonnes of annual pure hydrogen production, that would require a capacity of 700 gigawatts of offshore wind power, clearly something not achievable in the short to medium term, considering the current identified pipeline of all offshore wind potential stands at 500 gigawatts, which means that the offshore wind is not the only solution to the decarbonisation of hydrogen production, but it will play a significant role. And now, who invests in offshore wind? Our report takes a detailed look at leading developers and investors and the increased interest of mainly European oil and gas firms. The largest players are currently developers, owners and operators, DOO, such as Ørsted, RWE, including the former E.ON and Energy portfolio, China Longyan, the world's largest wind farm developer, and Vattenfall. Leading infrastructure investors, Macquarie and Global Infrastructure Partners, or GIP, OEM finance arms like Siemens, and federal and state pensions are also investing in offshore wind. The level of investment by oil and gas players in renewables has been comparatively low to date, generally less than 1% of total capital investment, with the leading players achieving around 5% of total investment in renewables. With up to an estimated 40% of the supply chain being complementary, large offshore wind projects, and even more so for floating wind, will benefit from project management and skills and large balance sheets of oil and gas companies. European players, including Equinor, Shell, Total, and Repsol, have all made investments in bottom-fixed and/or floating wind projects. China's CNOOC has investigated offshore wind projects to power its oil and gas platforms. The US majors are currently showing no signs of moving to offshore wind, focusing rather on carbon capture, utilization, and storage schemes, with some onshore renewables. So what are our key takeaways from this whole report? Offshore wind is growing rapidly from a low base. Offshore wind offers advantages versus fossil fuels and other renewables. Coronavirus impacts on offshore wind activity are somewhat less than for other sectors. Market penetration of offshore wind varies significantly by region. Opportunities to exploit offshore wind resources are huge. 1 trillion to 1.5 trillion of capex on offshore projects is required over the next 2 decades. Current pipeline will require up to $46 billion of annual OPEX once delivered. New players are entering the offshore wind sector as wind economics improve and support for energy decarbonisation grows. Costs for offshore wind projects are coming down, increasing competitiveness. Floating wind has moved to the stage of commercial development and presents significant opportunity. And winter hydrogen is emerging as a key enabler for offshore wind growth. So thank you for your time and interest. I trust that this has whetted your appetite to learn more about this exciting sector. Should you have follow-up questions regarding the material, please do not hesitate to contact us outside of the webinar. Thank you and have a good day.